Hello students, welcome to this lecture on vector Kalman filter. Let us recall the scalar Kalman filter uses the first order autoregressive signal model, that is xn is equal to a times xn minus 1 plus wn, where wn is a white noise and a is a constant. To tackle non-stationarity, a can be a function of n. The observation model is given by yn is equal to xn plus vn. Again vn is a white noise uncorrelated with xn and uncorrelated with wn. Kalman filter recursively estimates the signal. So that we know that Kalman filter recursively estimates the signal on the basis of the current and all the previous data. We derive the filter equations through innovation representation of yn. For data yn we had a innovation representation and then we derive the scalar Kalman filter. The following are the scalar Kalman filtering steps. First, calculate the mean square prediction error. This formula P of n given n minus 1 is equal to a square times P of n minus 1 given n minus 1 plus sigma w square. So, this is the mean square error estimated at time n minus 1. Then we calculate the Kalman gain kn, that is equal to P of n given n minus 1, that is the mean square prediction error, divided by P of n given n minus 1 mean square prediction error plus sigma v square. Then we estimate the signal. X at n given n is equal to a times x at n minus 1 given n minus 1. This is the predicted part and there is a correction part here into kn n, that is Kalman gain multiplied by the innovation part yn minus a times x at n minus 1 given n minus 1. This is the estimator at instant n minus 1. Then we update the MS estimation error. P of n given n, that is equal to 1 minus kn n into P of n given n minus 1. This is the step for updating the mean square error. Now we will extend the scalar Kalman filter to the vector case. The analysis is similar. We will state the salient results only. We will not go into detailed analysis, but this derivation is also based on the innovation representation of the data. Now we will introduce vector Kalman filter. As we have seen in the earlier, an ARP signal can be represented in a state space model. A state space model in general represents a linear time varying system and comprises two matrix equations, a state equation and an observation equation. This is the state space model used by the control engineers. The vector Kalman filter is a recursive estimator of the states of such a model in which states are driven by noise. We will show the model. States are driven by noise and observations are made in the presence of noise. So, that way we have noisy observations and we have to estimate the states. There are number of ways to derive the Kalman filter. For example, there is a Bayesian approach. We will present the approach of minimum mean square error estimation and outline the derivation through the innovation representation of a WSS signal. Let us discuss the state space model. This model arises from the pth order difference equation representing signal or a linear system. For example, in the case of ARP model, we have a pth order difference equation. Similarly, a discrete time linear system can be described by a pth order difference equation. Now, this state space model comprises of two equations. It comprises two matrix equation actually, matrix equations. Number one is state equation. This state equation is given by this xn is equal to an into xn minus 1 plus wn. So, here this is a first order difference equation, unlike in the case of general model where it was pth order difference equation, this is first order difference equation. Now, here xn is the state vector comprises of p state variable x1n, x2n up to xpn. So, this is the state vector, and n is a p by p because p dimensional state vector is there. So, an will be a p by p system matrix or state matrix. Wn is a zero mean noise vector with the p by p covariance matrix, that is qw is equal to E of wn into wn transpose. This wn, it is a noise vector which is also known as the process noise, and its state component will have corresponding noise addition, and this noise is a white noise and it is characterized by the covariance matrix E of wn into wn transpose. Since wn is assumed to be a white noise, qw is a diagonal matrix. So, this qw matrix is a diagonal matrix. In Bayesian derivation, wn is assumed to be jointly Gaussian also. In addition to white, this is assumed to be Gaussian also. Now, we will see the observation model. The observed data yn, that is comprising of y1, y2 up to y qn, there are q observation at a instant n. So, this is represented in terms of vector and that is the yn vector. It is related to the states by the observation equation, that is yn is equal to cn into xn plus vn. So, this is the observation equation, yn is equal to cn into xn plus vn. So, this is the observation equation. Now, here cn is a q by p output matrix because this yn is a q dimensional vector, therefore, this matrix is q by p matrix. Vn is a zero mean white Gaussian noise factor. This is the measurement error or measurement noise, which is also assumed to be white. Gaussian is necessary only in the Bayesian derivation, and its covariance matrix is a q by q matrix, which is given by qv is equal to E of vn into vn transpose. qv is a diagonal matrix because vn is a white noise vector. And further, it is assumed that vn is uncorrelated with both xn and wn. So, this vn is uncorrelated with xn and also with the state noise, that is wn. So, therefore, vn is uncorrelated with xn, that is the state, and the wn, that is the state noise or process noise. Now, let us see linear minimum mean square error estimation and linear minimum mean square error prediction associated with Kalman filter. Denote the L MMSE estimator by this x hat n given n. E hat is the symbol for linear minimum mean square error estimator. Therefore, x hat n given n is E hat of x n given all the data up to present y0, y1 up to yn. And the linear minimum mean square error predictor is given by this x hat n given n minus 1, data up to n minus 1. So, that way it is E hat of x n given y0, y1 up to yn minus 1. So, therefore, this is a one step predictor based on all the past data. Now, this quantity x hat n given n minus 1, that we can write as E hat of x n given y 0, y 1 up to y n minus 1. Now, x n we can write like a n into x n minus 1 plus w n. So, this is the state model we are using. So, using this state equation we will get the above expression is equal to E hat of a n into x n minus 1 plus w n given y 0, y 1 up to y n minus 1. And now, this is E hat of x n minus 1 given y 0, y 1 up to y n minus 1 is the LMMSE or linear minimum mean square error estimation of x n minus 1 given data up to n minus 1. So, that way it is x hat n minus 1 given n minus 1. Therefore, x hat n given n minus 1 is a n times x hat n minus 1 given n minus 1. So, this prediction is related to the previous estimation by this relationship a n times the previous estimation. We can find out the corresponding error covariance matrices also. Suppose estimation error E of n given n, that is equal to x n minus x hat n given n. This is the estimator of x n given data up to n. Similarly, E of n given n minus 1, that is x n minus the prediction, that is the prediction of x n given data up to n minus 1. So, that way this is the prediction error, this is the estimation error. Now, we can define the error covariance matrix. In scalar case, we are interested only in mean square prediction error, but here we will be considering the error covariance matrix. So, that way P of n given n, that is the notation for error covariance matrix. So, this is the estimation error covariance matrix and it is given by E of E n given n, that is the estimation error into E n given n transpose. So, estimation error vector into estimation error vector transpose. So, this is the estimation error covariance matrix. Similarly, prediction error covariance matrix we can find out, that is denoted by P of n given n minus 1. This is expected value of E n given n minus 1 into E n given n minus 1 transpose. This is the prediction error vector, this is the transpose of the prediction error. So, that way we get the two covariance matrices, that is P of n given n, this is the estimation error covariance matrix, and another covariance matrix is prediction error covariance matrix. So, that is given by this P of n given n minus 1, that is equal to E of E n given n minus 1 into E n given n minus 1 transpose. Prediction error vector into prediction error vector transpose. Now, let us see the innovation representation for the vector case. We know the innovation representation for the scalar case. So, the derivation of the Kalman filter is based on the innovation of y n, and which is given by this expression. Y tilde n is equal to y n minus the linear estimator of y n given data up to n minus 1. So, E hat of y n given y 0, y 1 up to y n minus 1. We have y n, this is the y n vector is equal to Cn matrix into state vector x n vector plus V n. V n is a white noise vector. So, this is the observation model that we are substituting here. So, this will be E hat of Cn into xn plus Vn given y 0, y 1 up to y n minus 1. and this will be, because now Vn, this is the noise which is independent of all past data, therefore, this part will contribute 0. Therefore, we will have Yn minus Cn into x hat n given n minus 1. Now, this quantity also x hat n given n minus 1, that is equal to An x hat n minus 1 given n minus 1. The prediction is obtained through the model, that is An into x hat n minus 1 given n minus 1. Therefore, y tilde n will be equal to Yn minus Cn, Cn matrix into An into x hat n minus 1 given n minus 1. This is the previous estimation. Thus, we have obtained the innovation of data, that is given by y tilde n is equal to Yn minus Cn into An into x hat n minus 1 given n minus 1. So, this has come through the model. We can use the innovation to get the recursive estimation of states. We have y tilde is equal to Yn minus Cn into An into x hat n minus 1 given n minus 1. Now, generalizing the scalar model, in scalar model we had x hat n given n, that is equal to a times x hat n minus 1 given n minus 1 plus kn n times the innovation. And here we omit this superfix n. So, simply we write kn. Therefore, x hat n, in this case it will be a vector now, x hat n given n is equal to that predictor part, that is x hat n given n minus 1 plus a correction based on the innovation, that is kn times into yn minus y hat n given n minus 1. This is the prediction, and this we can write as an into x hat n minus 1 given n minus 1, that is the estimation part at instant n minus 1, into kn times yn minus, and this we can write through the model Cn into x hat n given n minus 1. Now, we can write here also x hat n given n minus 1 is equal to an into x hat n minus 1 given n minus 1. Therefore, our x hat n given n will be an into x hat n minus 1 given n minus 1 plus kn times yn minus Cn into an into x hat n minus 1 given n minus 1, where this kn is the p by q Kalman gain matrix. This matrix weighs the innovation part. Thus, we can write x hat n given n is equal to an into x hat n minus 1 given n minus 1 plus kn times yn minus Cn into an into x hat n minus 1 given n minus 1. So, this is the state estimator for the Kalman filter. From this expression, we can have the Kalman filter structure. So, there is data here, data is yn, and the state estimator is x hat n given n. Now, this estimator is delayed by 1 unit and then multiplied by an to get the prediction x hat n given n minus 1. So, we will get here x hat n given n minus 1, given data up to n minus 1, we will get the prediction value through the delayed version of the state estimator. So, when we delay this, here we will get x hat n minus 1 given n minus 1, that will be multiplied by an, and we will get this prediction. And this result is multiplied by Cn matrix, and then we will get the predicted yn, that is y hat n given n minus 1. So, this is the prediction of the data vector at instant n because of the data up to n minus 1. So, this is the prediction vector. We can give a bar here to denote vector. So, that way this is the prediction vector, this is the actual data, and then difference is the innovation, and that innovation is scaled by the Kalman gain and then added with the predicted part to get the estimator. So, that way estimator has a prediction part here and then there is a correction part which is the innovation multiplied by the Kalman gain. Now, we will state the Kalman filter equation. The estimation of the signal is based on the recursive estimation of the error covariance matrices and Kalman gain. So, we will see how they are estimated. Following this same procedure as the scalar Kalman filter, we can derive the following Kalman filter equations, that is update of prediction error covariance matrix P of n given n minus 1 is equal to a n times P n minus 1 given n minus 1 into a n transpose. A n is the time varying system matrix plus Q w. Q w is the covariance matrix of the process noise. So, therefore, the prediction error covariance is given by this P of n given n minus 1 is equal to a n into P of n minus 1 given n minus 1. This is the estimation error covariance matrix multiplied by a n transpose plus Q w. First one is the update of the prediction error covariance matrix, and this is given by P of n given n minus 1 is equal to a n into P of n minus 1 given n minus 1 into a n transpose plus Q w, where a n is the system matrix or state matrix and Q w is the covariance matrix of the noise vector. So, that way we can find out the prediction error covariance in terms of the estimation error covariance of previous iteration. Then estimating the Kalman gain. So, for that we have k n is equal to P of n given n minus 1 which we obtain here into C n transpose, this is the output matrix transpose into C n into P n given n minus 1 into C n transpose plus Q v whole inverse. So, this part is a matrix and inverse of this is taken. So, that way the Kalman gain is given by the error covariance matrix multiplied by this output matrix output matrix transpose multiplied by this inverse of C n into P n given n minus 1 into C n transpose plus Q v. Q v is the covariance matrix of the observation noise. So, once we have the Kalman gain, we can update the estimation error covariance. P of n given n is equal to I minus k n into C n, this is the Kalman gain, into C n into P of n given n minus 1. So, given the prediction error covariance, we can get the estimation error covariance. Along with this equation, we must have the initial estimate, that is x hat of minus 1 given minus 1, and the estimation for P of minus 1 given minus 1, that is the covariance matrix of the mean square error, one estimate must be there. Now, given these initial estimates x hat minus 1 given minus 1 and P minus 1 given minus 1, the above equations, these three equations can be used to recursively estimate the state, and the recursive state estimator is given by this x hat n given n is equal to a n into x hat n minus 1 given n minus 1 plus Kalman gain Kn into Yn minus Cn into An into x hat n minus 1 given n minus 1. So, this is the innovation part and this is scale by Kn and added to the predicted part. With these backgrounds, we can now state the Kalman filter algorithm. So, here we have to know the state equation x n is equal to a n x n minus 1 plus w n. Observation equation, that is given by y n is equal to c n into x n plus v n. This is the observation equation. So, we must be given a state matrix a n for n is equal to 0 to p, because it is pth order system or signal, and the process noise covariance matrix is given by QW, which is a diagonal matrix. The observation parameter matrix, that is Cn, for n is equal to 0, 1 up to 2 if it is time varying, otherwise it will be a simply C matrix, and the observation noise covariance matrix is given by QV. This is again a diagonal matrix, and observed data Yn, that is from n is equal to 0, 1, 2, etc. So, these are the things needed for the algorithm. Now, it will be initialized as x hat minus 1 given minus 1 is equal to 0. All states are initialized with 0, and this estimation error covariance matrix at instant minus 1, there is no estimation. Therefore, this will be the covariance of the data itself. If we know the statistical model, we can use that, and here we can write it as sigma square into I. This is the estimator, and if we take this type of initialization sigma square into I, where I is an identity matrix, then the Kalman equations converges. So, that way this sigma square is a positive number which can be based on the estimation of this quantity, or we can assume some value. Kalman filter runs like this. For n is equal to 0, 1, 2, etc. First we will predict. So, predict the state, that is x hat n given n minus 1, that is given by a n into x hat n minus 1 given n minus 1. So, this is the estimated value. This predicted term will be used in the updating here. Then we will have to estimate a priori error covariance matrix or prediction error covariance matrix, that is given by P of n given n minus 1, and this is related to previous estimation error covariance matrix by this relationship. This is the state matrix A n into P n minus 1 given n minus 1 into A n transpose plus QW. QW is the covariance matrix of the process noise. So, we have the a priori error covariance matrix or prediction error covariance matrix. Now, we will compute the Kalman gain, that is given by this matrix Kn matrix, that is related to the error covariance matrix P of n given n minus 1 multiplied by C n transpose into inverse of this quantity C n plus P n given n minus 1 into C n transpose plus Q v whole inverse. So, this is the expression for Kalman gain. Now, once we have the Kalman gain, we can now update this state, that is x hat n given n is equal to x hat n given n minus 1, which we have obtained here, and then Kn times the prediction error Yn minus Cn into x hat n given n minus 1. This is the innovation or the prediction error. Now, after this we have to update the a posteriori error covariance matrix, that is given by P of n given n equal to I minus Kn into Cn into P of n given n minus 1. This is the a priori error covariance matrix, and this is pre-multiplied by this factor to get the estimation error covariance matrix or a posteriori error covariance matrix. So, this is the Kalman filter algorithm. It is a simple algorithm, but it is widely used. Some applications are as follows. Kalman filter has become an integral component of thousands of military and civilian navigation and guidance systems. So, any navigation or guidance system, Kalman filter is a part. NASA adopted the Kalman filter to solve the problems associated with determining satellite orbits, guided the Apollo 11 lunar module to the moon surface using this Kalman filter. The global positioning system GPS is based on this deceptively simple algorithm. Similarly, it can be used for video based tracking, time series based forecasting of financial data, etc. There are many applications, and there are many improved versions of this algorithm. Let us consider one example. Suppose a particle is moving with a random acceleration a n, which can be modeled as a white noise with variance 1. Acceleration is random with variance 1. We have to estimate the position of the particle in presence of the measurement noise, which is also white with variance 1. Let us solve this problem. Let x1 t and x2 t be the position and the velocity of the particle at time. These two will be the state variables. Assuming the sampling interval to be 1 second, we can approximately write, that is, position x1 n at time n is equal to x1 n minus 1, that is the position at time n minus 1, plus distance travelled in 1 second, that is x2 n minus 1, that is the velocity, multiplied by 1. Therefore, x1 n is equal to x1 n minus 1 plus x2 n minus 1, and velocity at instant n x2 n, that is equal to x2 n minus 1, velocity at instant n minus 1 plus the acceleration into 1, because after 1 second we are considering. So, that way this part we can write as x2 n is equal to x2 n minus 1 plus a n. The measured position of the particle is given by y n is equal to x1 plus v n. This is the observed variable, that is observed data y n is equal to x1 n plus v n, where v n is the measurement noise, which is given to be white with variance 1. So, we can write from these expressions x1 n is equal to x1 n minus 1 plus x2 n minus 1, and x2 n is equal to x2 n minus 1 plus a n. We can write the matrix states equations x1 n, x2 n, these are the states, is equal to 1 1 0 1, that is the system matrix, multiplied by x1 n minus 1, x2 n minus 1, these are the previous states, plus first equation we do not have any noise term, so that is 0, and second equation we have a noise term a n. So, this is the term corresponding to w n. So, this is the state equation. The observation equation is given by y n is equal to x1 n plus v n, because position plus noise, and this we can write as, because it is x1 n, so we can write it in terms of the matrix, that is a 1 0 matrix. This is a C matrix multiplied by x1 n, x2 n. So, these are the states. If I multiply, 1 0, that is the C matrix, into state vector x1 n x2 n, then 1 into x1 n plus 0 into x2 n, and we will get simply x1 n, and plus Vn. So, Vn is the noise, and it will have a variance because only it is a single dimensional quantity. So, it will have variance which is sigma v square, which is equal to 1. Thus, here we can write that Q W, that is a matrix, because it is E of this, if this is Wn vector, Wn into Wn transpose. So, that will be equal to E of 0 A n transpose will be 0 A n, and we will get E of, so 0, and this will be 0, and this one will be 0, and here A square n. If we take the expected value, we will get 1 here because variance is 1. So, that way it is 0 0 0 1. So, this is the error covariance matrix here. So, we know Q W, we know this is my A, which is constant, not time varying. This is my C matrix, and Q V is now a one dimensional quantity, that is equal to sigma v square, actually that is equal to 1. So, these are the parameters given. With this we can estimate the state. So, initial value we can assume that x hat minus 1 given minus 1, that is initially this is equal to 0, and then P of minus 1, that is error covariance matrix given minus 1, that will be also equal to some positive matrix we have to consider. So, that way sigma square I, where sigma square is a positive quantity, we may take, this is sigma square, we may take 1. So, we can take this as the identity matrix itself. So, this is 1 0 0 1. Now, starting with n is equal to 0, we will first estimate the prediction error covariance matrix. So, that way we will estimate P of 0 given minus 1. So, this is given by A into P minus 1 given minus 1. This is the initial estimate of the error covariance matrix into A transpose plus Q W. This is the expression. So, this we obtain from this expression A n into P n minus 1 given n minus 1 into A n transpose plus Q W. So, we get this expression, and we can carry out the computation now. This is equal to 1 1 0 1. This is my A, and then this is identity matrix 1 0 0 1, and this is A transpose. That way it will be 1 0 1 1 plus Q W. Q W matrix we have found out, Q W matrix is 0 0 0 1. So, that way it will be 0 0 0 0 0 0 1. So, we can carry out this computation, and we will get this as 2 1 1 1. So, this is the a priori error covariance matrix. Now, given this, we can find out K 0, Kalman gain at time 0, that is equal to P of 0 given minus 1 into C transpose into C into P of 0 given minus 1 into C transpose plus QV whole inverse. So, this is the expression we get from this formula. So, this is the Kalman gain. So, using this formula we get this. So, we have already obtained this and we have value of C is 1 0, here C is known, this one is known here, C transpose we know, QV is simply 1. So, that way we can write this as this is this matrix 2 1 1 1 into C transpose is C is 1 0. So, this will be 1 0 and here similarly this will be 1 0, this is the matrix, then this is 2 1 1 1 and then C transpose will be 1 0 plus QV is equal to 1 and whole inverse. So, this we can carry out and we will get the here this matrix. This is a 2 by 1 matrix, 2/3 and 1/3. Now, we can estimate x 0 given 0 that is will be equal to x 0 given minus 1. So, plus Kalman gain that is k 0 matrix into yn minus C times x 0 given that is y 0 here x 0 given minus 1. So, that way we can write and this part is 0 because there is no prediction initially, this part is also equal to 0 and therefore, we will simply have k 0 is 2/3 1/3 into y 0. So, that way this will be 2/3 of y 0 and 1/3 of y 0. So, this is the estimator for the states, this is the position, this is the velocity. Now, we can calculate P of 0 given 0, and that will be equal to I minus I is a 2 by 2 identity matrix into K 0 Kalman gain matrix into C all are given into P of 0 given minus 1. So, we know all this quantity. So, this is the identity matrix 1 0 0 1 and then K 0 we know that is equal to 2/3 1/3 this matrix. Then C we know C is 1 0 and then this P 0 given minus 1 that also we know that is given by 2 1 1 1. So, if we carry out this calculation we will get this as the 2/3 1/3 1/3 2/3. So, that way we can find out P 0 0, then we can find out P 1 given 0, then K 1 except 1 given 1 like that. So, we can estimate the states in this recursive manner. Let us summarize the lecture. The vector Kalman filter is a recursive state estimator for the state space model. This is the state space model. Xn is equal to an into x n minus 1 plus wn. An is the state matrix or system matrix. Xn is the state vector. Wn is the process noise vector. Yn that is the measurement vector or output data vector is equal to Cn, that is known as the output matrix, multiplied by the state vector plus Vn. Vn is the measurement noise vector. Wn is assumed to be white noise factor, thus the covariance matrix QW is a diagonal matrix. Vn is also assumed to be a white noise factor with the covariance matrix QV. Further, Vn is independent of Xn and Wn. The Kalman filter structure is given by the following block diagram. So, this is the input data yn and this is the x at n given n, this is the output state estimator. So, this is the input, that is the data vector. Now, this is delayed, that will give us x at n minus 1 given n minus 1, that will be multiplied by an and we will get the predicted part here, and this predicted part is multiplied by Cn to get the predicted data. Here we get the predicted state, here we get the predicted data. Then this is subtracted, we get the innovation. This innovation we are scaling by the Kalman matrix, and this is added to the predicted part to get the state estimator. Following the same procedure as the scalar Kalman filter, we can derive the following Kalman filter equations, that is obtain the update of the prediction error or a priori error covariance matrix P of n given n minus 1 is equal to an into P of n minus 1 given n minus 1 into an transpose plus QW. Estimate the Kalman gain, that is Kn is equal to P of n given n minus 1 into Cn transpose into inverse of this, that is Cn into P n given n minus 1 into Cn transpose plus Qv, where Qv is the covariance matrix of the observation noise. This is the covariance matrix of the observation noise. Then we will estimate the states, that is x at n given n is equal to an into x at n minus 1 given n minus 1. This is the prediction part plus Kn Kalman gain into one correction part, that is yn minus Cn into an into x at n minus 1 given n minus 1. This is the previous estimation. Now, we will update the estimation error, because here estimation error is used. So, for that we have to update it, and this update is given by I minus Kn into Cn into P of n given n minus 1. This is the covariance matrix update equation. So, this is the Kalman filter algorithm, and we are also stated that Kalman filter has diverse applications. Thank you.